Okay, yeah, so as I just mentioned, last week we spent a bit of time discussing Young's double-slit experiment. And this experiment was really interesting because it showed us that light does indeed behave as a wave, right? So we were able to show that the light waves passing through both slits interfered with each other. And when they interfered with each other, that produced the interference pattern on the screen behind it, okay? What we're going to see today is that similar interference pattern can be generated even if we don't have two slits. Even if we just have one slit, we can generate an interference pattern, okay? But producing an interference pattern, or producing that single slit diffraction pattern, requires the following. So it won't work. I mean, you could test this at home, right? Like if you have a doorway and you shine a light through it, there's going to be no diffraction pattern, right? The width of the slit determines whether or not you're going to get a diffraction pattern, okay? So the first criteria here is that the width of the slit is narrow enough that a substantial amount of diffraction can occur, but not so narrow that it just acts as a point source, okay? Another criteria, which we actually had with the double-slit experiment as well, the light source is monochromatic, meaning it has a single wavelength, lambda, and the light source is far from the slit. So we assume that when the light rays are hitting the slit, they're all running approximately parallel to each other, okay? So when all three of these criteria are satisfied, what ends up happening is we get a diffraction pattern that's produced on the screen located behind the slit. This is called Fraunhofer Diffraction. Okay, I'm probably butchering that pronunciation. It's an interference pattern that shows distinctive differences between the bright central fringe. So as we can see in this pattern here, we have a really bright, prominent central bright fringe, right? Whoops. This is kind of not quite what we saw in the Young's double-slit experiment. The Young's double-slit experiment was a little bit more gradual, okay? So, yeah, it shows shows much more distinctive differences between the bright central fringe and the darker fringes surrounding it, okay? So here's a little example of the interference pattern. The bright fringe right in the middle is called the central maximum, okay? And then around the central maximum are the dark fringes, also called minima. And then those dark fringes are followed by less intense bright fringes called secondary maxima. Okay, and then that pattern will continue to repeat itself as it goes. All right, so you'll get alternating dark, bright, dark, bright, dark, bright around that central maximum. Okay, and that's the interference pattern that we have. All right. Now, just like we did with the Young's double-slit experiment, we can find a whole bunch of relationships between the various quantities involved here. Okay, so and actually I think I have a second picture down here. Yeah, so what we want to do is we want to try to relate all the quantities in this picture here. Okay, so we're defining the width of the slit to be W. Whoops. We are defining the angle between the central bright fringe and, say, a dark fringe or a bright fringe to be theta n or theta sub m. And then the spacing between adjacent dark fringes or between adjacent bright fringes we're going to call delta y. Okay, so these are all the quantities that we're playing around with. I think for the most part, these are similar to the way that we defined the double-slit experiment. Okay, the difference being with the double-slit experiment, we talked about the spacing between the two slits. I think we used x sub n to describe the distance between the perpendicular bisector and whatever order bright or dark fringe we were looking at. So the variables might be a little bit different here, but the idea is kind of the same. Okay. Oh, and last, I think I don't have it printed on this picture, but we're also going to be using the distance from the slits to the screen. We're going to be calling L. And I think that's the same definition as we had for the double-slit experiment as well. Okay, so let's walk through these formulas really quickly. So these first two formulas describe how we can find, or where we would find, the dark fringes. So this first formula here is for dark fringes. The second formula here is for the bright fringes. Okay, very similar formula. The only difference is, notice that so the right hand sides of these formulas represent the path length difference. And notice that the dark fringes have integer wavelengths for the path length difference, whereas the bright fringes have half integer wavelengths for the bright for the path length difference. Okay. And then we can also define a formula for the spacing between the two spacing between adjacent bright or dark fringes. Okay, so that delta y that we saw in the picture before. Okay, so delta y is the distance between, say, a dark fringe and the next dark fringe, or a bright fringe and the next bright fringe. Okay. Whew. So lots of formulas, but again, I think this becomes easier the more that we practice. Okay. Does everyone have these formulas jotted down? Take a second. Take your time. I actually forget if I posted this. I'll post these notes on Edsby just so you have them as well. Let's see here. Tuesday. Yeah, Edsby is being increasingly slow, day by day, just continually bad. So the notes are uploading. I'll click share when it's ready. Okay, so now we're going to use all of these formulas to answer some problems now. Okay. Any questions behind the whole setup here, or are we all doing pretty good? Okay, so example. Light with a wavelength of 5.40, so that's 540 nanometers. Okay, so the wavelength is 540 nanometers. Is incident on a slit, and the slit has width 11 micrometers. Okay, so that is W equals 11. Whoops. 11 times 10 to the negative 6 meters. Okay. And produces a diffraction pattern on a screen that's located, so the screen is located 80 centimeters behind the slit. So that is L is 0.80 meters. Okay. We have to calculate the distance of the first dark fringe from the maximum on the screen. Okay, so distance of the first dark fringe from the central maximum. All right, so just to draw a quick picture of what we're finding here. So we are going to have the notes finally uploaded if you want to take a look at any formulas. But again, so we have this diffraction pattern, right? And we have this very bright, let's try to make that a little bit nicer. We have this broad central maximum. And then adjacent to the central maximum are these dark fringes. Dark fringe. And it's the first dark fringe on either side. Okay. And then this right here is the central maximum. What we're interested in is the distance from the central maximum to the first bright fringe. The first dark fringe. So here we're looking for delta y. All right. So what is delta y? Okay, so for that, we're going to be using our lambda equals W delta Y over L formula. right, and I'm going to rearrange this for delta y. So lambda times L over W equals okay, so now I can plug, yeah, so Costa, just like you mentioned, this is 540 times 10 to the negative 9 meters. All right, so now I'm going to plug everything in and see what we get. So 540 times 10 to the negative 9 times L, which is 0.80, over the width, which is 11 micrometers. Okay. So delta y will be 0.03927727 meters, okay, or approximately 3.9 centimeters. Okay. .9 centimeters. Yep. Okay. I'll pause here. Okay, so next example here, very similar, except that we are going to be talking about angular width. So we're going to be bringing angles into this. All right, so but same kind of setup. Light with a wavelength of 670 nanometers. So 670 nanometers equals 670 times 10 to the negative 9 meters. Is incident on a slit with width 12 micrometers. So W equals 12 micrometers, which is 12 times 10 to the negative 6 meters, and produces a diffraction pattern on a screen that is 30 centimeters behind the slit. Okay, so that's our L value, right? L equals 30 centimeters. Which is 0.3 meters. Okay. So the first thing we have to do is calculate the angular width and the absolute width of the central maximum. Okay. And so what that means, again, drawing out a quick sketch of what's going on here, we have our central maximum will look something like that, right? What we're interested in is the angular width of the central maximum. So we want to know theta here. Our goal is to figure out what theta there is. Okay, so the angular width of the central maximum. And we also want to know what the absolute width of the central maximum is. So we want to figure out what this value is here. Right? So now this value, again, going back up to the picture that I had up here, delta y describes the spacing between adjacent bright or dark fringes. Okay, delta y also describes the half the width of the central max. Okay, which means that the entire width of the central maximum is equal to 2 delta y. Okay, so this will allow us to find the absolute width of the of the central maximum. Okay. So let's give this a go. Okay. So again, going back up to my my formulas here, right? I know that the dark fringes are given by this formula right here. So W sine theta n equals n lambda. All right. And if I'm considering the angular width of the central maximum, what I need to do is I need to take the first dark fringe on either side, right? So I'm going to make n is equal to 1 in this formula and solve for what theta is. All right. So let's give it a go. W sine theta 1 equals lambda. Okay. So again, that path length difference is a multiple of whole wavelengths, right? Now I can rearrange this thing for theta 1, okay? But I have to keep in mind that theta 1 in this case is only giving me like half the angle here, all right? So what I'm going to have to do once I find theta 1, I'm going to have to double it to get the full width, okay? Because again, theta 1 in this case just represents the angle from like my midline out to the first dark fringe, okay? So I'm going to have to double that to figure out what theta is, okay? So theta 1 equals lambda over W, and then sine inverse of that. Times 10 to the negative 6, and I get a value of about 3.2 degrees, right? And so again, that's fine, right? Finding that value is good, but again, what I have to do from here is I have to double it to find the full angular width of the central maximum. Okay, so theta, the full angle here, is equal to 2 theta 1. So 2 times 3.2 degrees, or approximately 6.4 degrees. Okay, and yeah, that's that. All right. So I found the angular width of the central maximum. Now I can find the absolute width of the central maximum. Okay. So again, for that, I need to figure out what delta y is, and then once I have delta y, I just double it. Okay. So again, going back to my delta y formula, I'll actually just steal it from the previous question. All right. So delta y is equal to okay, so let's solve for delta y here. So delta y is our wavelength. So 670 times 10 to the negative 9 meters times L, which is 30 centimeters, so that's 0.3 meters, over our width, which is 12 times 10 to the negative 6 meters. So I'll plug that in, see what we get. I get a value of 0.01675 meters. So that's approximately equal to 1.67, or not approximately, is equal to 1.675 meters, centimeters. But again, I have to double it, right? Because this only gives me half of the width of the central max. So I have to double this. So 2 delta y will be equal to about 3.4, approximately 3.4 centimeters. Okay, and that's that. So we found our angular width of 6.4 degrees and our absolute width of 3.4 centimeters. All right. Alrighty. Now, the cool thing about what we've just found is that we've actually answered the other two parts of this question without even having to do any extra work. All right. So calculate the distance between the first and second minima. Okay. Well, again, going back up to our pattern here, the distance between adjacent minima is just given by delta y, right? So delta y tells you how to get from one minima to the next or one maximum to the next. All right, so we've already calculated this, which means the answer to part B here, calculate the distance between first and second minima, that's just 1.7, right? Or yeah, approximately 1.7. So from this, B, the distance between the, what was it, second and third? First and second minima? First and second minima is delta y, which is equal to approximately 1.7 centimeters. All right. And the distance between, again, going back up to part C here, determine the distance between the second and the third maxima. Again, that's just delta y, right? So part C, the distance between the second and third maxima is also delta y. All right, so it's a very nice symmetric pattern, and it repeats uniformly. Okay, so that's pretty cool. I'll take a pause here. Okay, so now let's get into something slightly different, but it's almost the same in the way that we're applying these formulas. So a diffraction grating is a device that has a large number of equally spaced parallel slits. Okay, so I was trying to think of like a way to describe this. Basically, actually, let me see if I can pull up an image of one. I mean, the cool one cool example. Okay, so let's get back to it. So again, yeah, diffraction grading is a device with the large number of equally spaced parallel slits, and when we shine light on that diffraction grading, it produces a interference pattern. Costa, your microphone's pretty loud. It's you. Okay, let's try this again. Okay, so similar to the other interference patterns that we've discussed so far, there's a pattern of bright and dark fringes. Okay, so the maximum intensity. Okay. Yeah, so the other interference patterns that we've discussed so far, we have a central bright patch, right? A bright fringe. The maximum intensity when theta is equal to 0, so right in the center of our pattern, we call the zero order maximum. Okay. And then the next maximum occurs at a certain angle away from that. Again, the path length difference is equal to the wavelength. So the first order maximum is found using this formula, right? We can find the angle that the first order maximum is found at, okay? And then the pattern continues, right? Each consecutive maximum is found by just adding a wavelength to the path length difference, okay? So this ensures that the waves are constructing, or the waves are interfering constructively, meaning we're going to get another maximum at these locations, all right? So only two formulas for this. When a question refers to the order number, it's essentially defining what number maximum we're looking at. Okay, so a zero order maximum is the one right in the middle, and then the first order maximum is the next one over, second order maximum is the next one over, so on and so forth. Okay, so let's do an example. Light with a wavelength of 540 nanometers. So 540 times 10 to the negative 9 meters is incident on a diffraction grading. And now this is a little bit strange, the way that they're describing this. So the diffraction grading has 8,500 lines per centimeter, okay? And so what that's telling us is it's actually, it's a way of encoding information about the width of each opening, okay? Because the width that we have here, the width that we're defining in our two formulas up there, that's the width of each individual like spacing in our diffraction grading. Okay, and so what we have to do first is we have to kind of untangle this value here. I'm going to give this a name though. I'm going to call this value n. Okay, and n is just the number of lines per centimeter. Okay. And so what I can do is I can use this to figure out the width of each line. All right. So if I do the width equals 1 over n. Okay. And let's see why this is true. So if I do 1 over 8,500 lines per centimeter, then when I flip this around, I get 1 over 8,500. So I get 1.17647, keep a couple extra digits, centimeters per line. All right, so my units flip as well. All right, so this tells me how, oh, and I forgot my times 10 to the negative 4. Okay, that makes it seem a lot more reasonable. So this tells me the width of each and every single one of those lines. Okay, so you can see immediately here that the lines are very, very, very narrow. Okay, and there's a ton of them just kind of stacked right next to each other, and that is what a diffraction grading is. Okay. But I need to also convert this to meters, so I'm going to divide by 100 here. So I get 1.17647 times 10 to the negative 6 meters per line. Now I'm all set, right? So this is my W value, right? I found the width of each line, all right? Okay, and then we have to figure out the angles, say, of the first and the second order maximum. Okay, actually, we're gonna try to calculate as many maxima as we can. Okay, and we'll see how many we get. All right. So the first order maxima, so theta 1, we can find. So first order. So in the first order, m is just equal to 1. Okay. So let's figure out what the angular width is here, right? So we get lambda equals w sine theta 1, and we can invert this to figure out what theta 1 is, right? We're looking for the angle, okay? So let's figure this out, lambda over w, and then we do sine inverse of that is theta 1. So theta 1 is let's see what we get. I get a value of about 27 degrees. Okay, so we found our first the angle to our first maximum. Now let's keep going, right? Let's try to find our second order maximum. All right, so same idea, except we're gonna make any m equal to 2, so second order. All right, so same idea, lambda equals w sine theta 2. All right, so theta 2 equals sine inverse lambda over w. Oh, I forgot 2 lambda, right? Is that the formula? M lambda, yep. So really I want 2 lambda over w. All right, and then we'll plug in and we'll solve. I get a value of approximately 67 degrees. Okay. So now I'll switch over here. So when you compute the piece inside the bracket here, right, the 3 lambda over W, Costa microphone. What you end up finding when you compute 3 lambda over W, so 3 times 540 to the power of -9 over W, 1.17647 x1 to -6, you get a value of 1.377, okay? Now, we know that sine only goes between -1 and 1. What we found here is a value that's bigger than 1, so there's no way of finding an angle that works for it, right? This is outside of the range of sine, so there's no value of the domain that gives you this. And so what this tells us is that there is no third order maximum. The diffraction pattern does not contain a third order maximum. It's impossible, okay? So really there's the 0 order maximum, the first order maximum, and the second order maximum, and that's it. That's what our pattern consists of. There's no other maxima beyond that, okay? Cool. Okay. One more example and then we're done for the day. All right. So, light emitted by a particular source is incident on a diffraction grading. And again, we're given the number of lines per centimeter. So n is equal to 9,000 lines per centimeter. And we can flip this around. So the width of each line is 1 over n. So 1 over 9,000. So that's 1.11 repeating times 10 to the -4 centimeters per line, which is put into meters, 1.11 repeating times 10 to the -6 meters per line. Okay, so we have our W value, and it produces a first order maximum. So when m is equal to 1, theta 1 is equal to 32 degrees. Okay. Now, using this information, I'm going to determine the wavelength. All right. So let's figure out what lambda is. All right. And so this, I just used the same formula that I have been using. Right. Lambda is equal to W sine theta 1, which means we can just plug in values right away. And we get a value of 5.88799 times 10 to the -7 meters, which is 589 nanometers. And that is the wavelength of light that's incident on this diffraction grading. So I would say, I don't know about you guys, but I would say diffraction grading is, I don't know, it's pretty straightforward, right? There's really only one formula that we apply, and the formula itself is pretty straightforward. The only maybe tricky bit is having to figure out what W is first, but even then it's not so bad.